I like to break things. It's good that we have Josef Machytka from Creative who knows how to fix things. Over to you.
Yeah. Thank you very much. It's good to be here, and I thank all of you that you came to this very last talk, and I hope it will be interesting for you. I can also, at least some of you, offer my beloved souvenir from conferences. I do these 3D printed elephants. Unfortunately, I had limited space in luggage in plane, so some of you can grab a 3D printed elephant, you know, Postgres in many shapes and colors fitting every use case, so at least few of them are here. I work for German company Creative, and we support open source products, and Postgres is one of our biggest topics, and we have really great experts, so we would be happy to welcome you as our customers, because I think we can together do a lot of good things. One thing which I would like to advertise here is our new open source migrator for migrating from 8 different proprietary or commercial databases into Postgres. It's open source, you can test it. Here are a few words about me. I have more than 30 years of experiences with different databases, worked in different environments with different technologies. I am originally from Czechia, now living 12 years in Berlin, and lately I was quite active on conferences and meetups with my talks. I want to remind us words of Simon Riggs, which he said on the conference in Prague in December 2023. And he urged the community to not be too satisfied with the situation that Postgres is #1, because we still need to ask stupid questions, he said. And he specifically pointed those are good questions. And this is why I started to ask stupid questions about database corruption, because I had to repair several corrupted databases, and it was really interesting learning. But first of all, I want to acknowledge that there are already amazing talks about these topics and some articles, and I built on these things. Without them, my talk would be completely different. So if you need information about data corruption and how to repair it, and you want to go on practical side more, I highly recommend this stuff. Those are clickable links. You can find it in my slides later. But I also must say that on Linux, Postgres is actually typically remarkably stable. All those crash databases were on Windows, except for Windows, I know. Except for one cases when a Kubernetes cluster damaged data on persistent volumes. So it was not because of Linux, it was because of Kubernetes. And in all those cases, they had no useful backups, so I had to go very deeply into repairing this stuff. And what is important to understand, we all can have corrupted data in database and not knowing about it. Because if we use typical binary backups, which are based on PG-based backup tool, this tool backups binary data as they are without checking data content. So we can have tons of backups with corrupted data and not knowing it, because if we do not select directly those specific corrupted data, that corruption is not revealed to us. This is why all these corruptions have been revealed during PG dump backups, and I gathered here several examples. Typical is like invalid page in some block. We can also see this very well-known cannot access status of some transaction with some ridiculous number, or PG dump cannot read data from sequence. And in some very rare cases, that session which reads data can even crash with memory segmentation fault. And I will show you why this is happening. Of course, this means that PG dump stops and does not back up anything. but we can write very simple script which will go over all databases, all relations in those databases, and dump each table separately, one by one, and redirecting errors into a file. And that way we can dump those tables which are okay, and we can pinpoint those problematic objects. Postgres in current versions stores everything as heap tables. So all objects can be corrupted in a similar way. We will just see different error messages. And since I have seen very strange behavior in those all cases, I decided to create corruption simulator, quite simple Python code, which surgically damages specific parts of a data block and allows me to test what is happening in such situations. But fortunately, there is big change coming in Postgres 18, and those are checksums which will be set on by default, and here is that commit which actually did it. In previous versions, those checksums have been switched off due to performance concerns. We can, of course, use this PG checksums tool, which can activate checksums on existing clusters, but it requires some downtime, and for some databases, it could be quite long downtime. So we will still see thousands, maybe millions of databases running without checksums in years to come. But since we have this nice feature with checksums, let's look at it, what it actually does when something happens. So as we all understand, Postgres calculates checksum for that data block, which should be stored on the disk. Value is stored in the header, it is flashed on disk, and later when we read back data from the disk, Postgres calculates checksum again, and if there is a difference, we get this page verification failed error. And it is following with invalid page in block number error. And query stops. This is default behavior, which we can influence with this ignore checksum failure parameter. By default is off. If we say do ignore, we switch it to on, then we will see multiple these page verification failed errors until query reads either all damaged data blocks or find some data, and then it will give us result based on those data blocks which are readable. We have a way how to get rid of those damaged data blocks, and here is this zero damaged pages parameter. Again, by default is off, which means query will stop on the first error. If we set it to on, we will see a different behavior, and those invalid pages will be so-called zeroed out. It does what it says. It really will fill that block with zeros. So we will have now suddenly 8 kilobytes of zeros. And this page, which is so-called zeroed out, will be stored on disk, and later Vacuum can remove these pages. We must understand that this is actually like just way how to allow us to use data which are not damaged, but those damaged data blocks cannot be repaired that way. They are simply removed. So we can continue our operations. And this operation is cannot be undone. Even if we set zero damage pages to off, those pages which were already zeroed out, they will stay zeroed. So we must understand what we do, but in many situations, this is the only way what we can do. This zeroing out in code is actually in buffer manager, so if a page is not verified, here is this memset command which will really which will fill that the data block with zeros. And here comes the question, what about auto vacuum? presuming we have damaged blocks, we set 0 damaged pages on, what will auto-vacuum do? Fortunately, it is done in a clever way, because otherwise, if it will act the way we see in front end, we would just lose data behind the scene, not knowing about it. And those will be damaged data, of course. But we would have suddenly a mystery in our hands where the data are gone. So as you can see here in code in auto-vacuum, it is forcibly set to off. And there is explicit note, we don't really want such a dangerous option being applied non-interactively. So we will zero out only those pages which we will actively scan with our queries. Auto-vacuum will not do this stuff. That was the better part of those damages, because those checksums can do this all work for us. But what about older databases which don't use checksums and which can be also damaged in some way? Here is data block, as we all know it, love it, hate it, whatever you feel about it. But this is current situation, how we store data in Postgres. And every part of this data block can be damaged. So let's start with header. If we don't have checksums, then corrupted header is the only situation when Postgres without checksums can actually detect problem in data page. As you can see here, this table from documentation, here are some values which actually contain some offsets and size of data block and so on. And if we look into code, there is this very interesting test and very interesting comment. What it generally does, it checks if those offsets are in proper relationship one after each other, and if those flag bits have some expected values. But that comment is really interesting. The following checks don't prove the header is correct, only that it looks sane enough to allow into the buffer pool. This is the reason why checksums are really, really important for us. Because without checksums, this is just a guessing game. We can have those numbers distorted, but they will be distorted that way that they will fit into this check, and code will say, okay, this is all I can say. That block looks sane enough. Here are these flag bits, which have only few values, quite small numbers. So if that those flag bits will be corrupted, this will be quickly found out. But again, in some cases, who knows? I did some analysis using extensions. So here you can see how healthy page header looks like. We have these offsets, lower, upper, special page size, version of data block layer is important, and these numbers in healthy data block fit that check. If we corrupt them, then there is nothing to be diagnosed. We simply get that invalid page error, and if we say 0 damage pages on, then header is zeroed out, and all damaged data are gone. So this is a better situation for us when header is clearly damaged. It does not pass that test, and code says, well, something is not good, so let's make that page invalid. But we can have situation when header is actually intact, contains values which are expected or at least fitting into that test, and we can have damaged item IT array. As we all know, this item ITs, those are pointer to the beginning of tuple, and they contain length of the tuple. So we add tuples from the end of data block, and we add new item IDs here after the header. And if we look at healthy data page, we see situation which is shown here. And as you can see, first tuple has the biggest offset to the start of the tuple, and each subsequent tuple has lower and lower offset because we are coming closer and closer to the beginning of data block. And here is length of those tuples because that table contains some variable strings. So those lengths of each of the tuples are different for each tuple. And yeah, here is CTID, nice and clean, how we expected, everything perfect. What if we damaged item IDs? We see situation on this second part. And you can immediately see the issue here. We have 8 kilobyte data block, and we have offset 20 kilobytes, 17 kilobytes, and length of that tuple, 28 kilobytes. Of course, code in Postgres takes these numbers as they are and tries to apply them. First of all, if it would have check for length of data block, I can imagine that it could actually slow down big operations. And second, as I said, Postgres on Linux is remarkably stable. But this is the moment when that memory segmentation fault can happen, because if that code reads that tuple starts somewhere 30 kilobytes away and it's 30 kilobytes long, then yeah, it does not fit in 8 kilobytes of that memory area for that data block. I tried to diagnose it with different tools. One of them is extension AMCheck. Unfortunately, it returns very cryptic messages and it does not raise any flag. Here, when we understand topology of a data block, we can immediately see that those numbers are ridiculous. Unfortunately, AMCheck does not raise a flag. It gives us something which looks like rocket science. So maybe there is some room for improvement to give like clear warning that something is wrong with that data block. That was situation with corrupted item IDs. But we can have another combination. Header is intact, item IDs are intact, but that area with tuples is damaged. And here it gets really interesting, because as we all know, each tuple has this header with very important columns, and especially transaction min, transaction max, they are really, really important for our multi-version concurrency control system, because they decide about visibility. So let's play a game further and let's damage those tuples. And I took example from toast table, because typical page in toast table has actually very nice structure, like having 4 tuples, each 2032 bytes long. And as you can see, all those tuples have been inserted with one transaction, and CTIDs are what we expect. And if we surgically damage tuples, what we see? We see situation here on that second part. As you can see, those offsets and lengths of tuples are okay. So we are able to go perfectly nicely for those tuples. And now when we try to interpret content of those damaged tuples, we suddenly see absolutely strange, absolutely crazy numbers. And this is the reason this really random content in those xmin, xmax, this is the reason why we get this strange error, could not access status of transaction with some strange number, all multi-transaction ID has not been created yet, apparent wraparound, or concurrent insert in progress, and so on and so forth. What happened to our Postgres? Well, nothing happened to our Postgres. Our tuples are damaged. And this strange content in those tuples is interpreted by Postgres code as it is. So we now see all these warnings, errors, and everyone is crazy. What has happened? What is wrong with my transactions? Nothing is wrong. You can have one damaged tuple inside table, and the whole table can be unreadable because of this cannot access status of transaction or whatever. And this is all because of damaged content in those system tables, those system columns in tuple. I looked directly in toast table, but if you select data from the main table and it reads data from toast table, then you can see another variety of these errors about chunk numbers, missing chunks, non-existing, whatever. This is all because of damaged tuples in that toast table, and we can see a lot of these things. So what we can do in these situations? Yeah, well, hopefully we all have some valid backups and we can restore it. But as I said, in all those situations which I had to face, there was no useful backup for whatever reason, or those backups have been damaged in exactly the same way because they were binary backups. So we have some options. Here I show example with PG surgery extension, which exists since Postgres 14. That's amazing, but on older Postgres we don't have this nice tool. So we have option either to freeze that particular tuple to get rid of those strange errors about transaction IDs, or we can kill that tuple. So let's first try to freeze it. Here is situation after freezing first tuple, and yeah, transaction IDs are nice. CTID, what we expect, but as you can see, those other columns are still damaged. So freezing can help us to not get those transaction ID errors, but we will still read some ridiculous data, some gibberish data. So freezing is not exactly our friend because we cannot be sure about the remaining content of that tuple. So it's better to kill those tuples. Extension kills tuples one by one. So if you have situation then when only few data blocks are damaged, you can do it using some script. As it is shown here, it works with CTID, but it must be CTID based on a real number of that page and order of that tuple in that data page. So that way we can remove those tuples. It would be probably nice to have some additional function which can kill the whole data block. It would help us to make these things quicker. But even this function is a good friend for repairs. Very quickly about sequence, because sequence is simply not transactional table with just one data block and just one row. So it has one tuple with all those hidden system columns and 3 normal columns, and one of them is last value. So it can be damaged exactly the same way. We just will see some nice error messages in some situations, like bad magic number in sequence. I like this error message for its contents, but it generally tells us that our sequence is damaged beyond repair. So in PG dump output, you will usually see an error message that that sequence return 0 rows. So we, without valid backups, cannot restore original data, and without checksums, Postgres can detect only situation with clearly corrupted header, and these cases can be zeroed out. Any attempts to somehow reconstruct damaged data, I think, are futile by definition, because first of all, Postgres stores tuples absolutely randomly, so we cannot be sure about content of that particular tuple because it's not in sequence or in many cases it's not. And therefore, we can only salvage good data from those tables or kill those bad tuples as I showed previously. That salvaging of good data is necessary in situation when we have a really big amount of damaged data blocks, and we usually do it using some scripts. And in those talks which I showed at the beginning, you can see more details. I just put here some idea how to do it because it's of course more complicated than this. Here is a very simple example which presumes that damage is in toast table, and I can read primary key values from that main table and then select data from that main table plus toast table using that primary key value. And when selection is successful, I immediately insert it into new table with the same structure and commit after each insert, because there could be this memory segmentation fault. So without a commit after each insert, we can actually face the situation, and after a few hours of run, everything crashes because of this memory segmentation fault. If this happens, we must find those IDs which are crashing. This script excludes them from that select, so as you can see, it's more complicated than just this simple example. But if we face a situation that we cannot read that primary keys from table because table itself is damaged, the only way how to read data is using CTID. So we must do two loops and we must calculate total number of data pages in that table, and we must find out or guess what could be the max number of tuples in the data page. And then we try to select really constructing CTID one by one. Data page number starts from 0 and tuple number in page starts from 1. This is interesting inconsistency in data storage of Postgres, but it is as it is. As you can imagine, this is not exactly a quick solution, but in many cases, this is the only solution which is left. If data are damaged, backups are not useful, and the damage is so big that we can only try to read what is readable. And again, if some CTID will cause that memory segmentation fault, we must exclude it from this select. So if we salvage data or delete wrong data from the database, we then face data inconsistency. And it means, of course, that foreign keys will be most likely compromised, and we need to decide if to delete orphaned rows from child tables or insert dummy rows into parent table to keep those records in child table. We must reindex indexes once our tables are readable, and if we have corrupted sequences, we must drop them and recreate them and set that last value based on data in those tables. But if we have corrupted system catalog, in that situation we can only install new installation of Postgres of the exactly same major and minor version and copy data into this new installation, because trying to somehow repair system catalog, I think this is something we really don't want to try. And this installation of the same version is not that difficult even on Windows. We just need to make some magic with those services, background services on Windows. So we had this situation also. This is almost everything I wanted to show you, but I will probably spend more time on this slide because I was discussing these cases when repair of data or salvaging of good data is really time-consuming, really annoying, and clients are really unhappy because their business is, frozen. So I understand that for normal run of Postgres, everything I propose here would be actually problematic because it would slow down the normal processing. But if you face something like this, that you have to, run business again, and the database is damaged, and there are some experts, in quotes from your perspective, who are saying, oh, it will take several days, then you would, as that entrepreneur, give a real gold for something like this to be able to very quickly resume operations. So maybe we should think, because we now will have those checksums by default, so everything will be easier for Postgres 18 and newer versions, but there will be still millions and millions of databases which can be damaged, or they are already damaged and their owners just don't know about it. And they could really benefit from some extension or something which would allow to quickly avoid these errors, like especially those error messages with transaction ID. I think that we must also trust users that if they would decide to use such tool, that they are doing it on their own risk. But it should allow them to skip these error messages, to really check for those ridiculous values in offset and length of tuple, to not jump into that memory segmentation fault, or at least some updates in pgdump, which would really help to dump quickly whatever is left, what is usable. So we can actually restore database into running condition. We can work on making it consistent, and client will have immediately bigger faith in running business quickly again, because some of those situations were really bad. One case was even caused by ransomware, and you can imagine how stressful situation it was for people in that company. So unfortunately, I am not the programmer, but I think many people who face this situation with damaged data would be really, really grateful to Postgres developers if they would think to allow something like this for quicker and easier repairs. Lost data are lost. We cannot resurrect them without backups. But in many cases, those damaged data have been actually some historical data or audit data, or something which was not that critical for the business, but not running database was absolutely killing that business. So this is something I think would really help people who are using Postgres, and sometimes even not knowing that they are using Postgres, because Postgres is in these days embedded in some Windows applications like DaVinci video editor, or different accounting software and so on. So those people are users of Postgres without knowing it, because they just use some front-end application. And that's all I wanted to show you. So I was deliberately quicker because, first of all, you can have some questions, and second, you may be in a hurry to catch your flight. So thank you very much.
We got an ample 15 minutes for questions, so don't be hesitant.
In PG18, if auto vacuum encounters corruption, will it write out somewhere or have some statistics we can monitor?
Yeah, this is a good question, and I unfortunately did not test this part. I was just making sure that auto vacuum will not do something behind my back, but I presume it should at least report these checksums errors. Not sure if it will crash. I must check it in code. Yeah, sorry.
How about PG backup? How about PG backup? The same question.
PG backup, like you mean base backup? Yes. Yeah, well, it does binary backups, so it takes data files as they are and copies them somewhere when you store that backup. So it does not check the content. These all errors are revealed only when you really read data from those data blocks. And this is the reason why people can have, like, you know, false feeling of being okay because I have backups. Yeah, but all those backups can have the same corruption.
Is it theoretically? Oh,
yeah.
Is it?
Who is talking?
Yeah,
Yeah, sorry.
Is it theoretically possible for a page checksum to pass, like to be valid, but for there to still be corruption and just like the perfect way to make it work, or, you know, even if it's theoretically possible, is it like, could it be likely to come up in practice in any, you know, maybe gigantic table?
Yeah. This is a very good question, and we had actually this discussion in Berlin on Meetup where I presented this talk for the first time. You know, mathematically everything is possible. Probability is a different thing, but you know, you have seen that code which checks if that page header is valid or not. So we are already facing a situation when we don't really know if our data are okay, because those corrupted values can actually pass all those checks, you know. Header can look intact, those transaction IDs, even corrupted, they could look intact, and we will get some gibberish content from those tuples which will look intact. So probability is probably very, very low, but you know, mathematically everything is possible.
So you mentioned that checksum has been enabled by default in Postgres 18, but there is some overhead in calculating the checksum, right? So is the overhead getting better in Postgres 18, or is it the same as it was before? And how much is it normally based on your experience?
Yeah, this is a very good question. Thank you. I wish my colleague Patrick would be here because he is a real guru around hardware. We discussed it, and he generally told me that with modern hardware, we are in a completely different situation than a few years ago. And there is also this improvement for asynchronous I/O in Postgres 18. So at least that reading will be much, much quicker. So I presume that overhead for calculating checksums in memory once it's read into memory will be so small that it will be actually lost in this improvement.
The overhead will be the same as before. The bigger burden is that you have to wall log all hint bits.
Okay, so here is even better answer. Yes?
My question is which is the best strategy to avoid having data corruption?
I'm not sure if I understood properly. So you are asking what is the best strategy to avoid data?
I mean, once you have data corruption, you have a huge problem. So there are methods internally. So, for example, you have full page writes in the wall files and these kind of things to avoid half page writes and so. But if finally, if the storage fails, redundancy at the storage level, having a replica that you can use to compare with the storage, both.
Yeah. This is important question. Thank you. I would say everything depends on how valuable data are and what strategies you can actually use to improve your certainty to not have corrupted data. So I think nothing is bulletproof, of course, but I am not that big expert on hardware as my colleagues. So if you would want to discuss these things in detail, I definitely advise to contact us, and our colleagues will tell you more. But I have seen these situations with those corrupted databases, and in many cases they said, okay, just restore what is okay, and let's forget those damaged data. So in many cases this is like the best strategy, because there is always this 0 point whatever probability that something will go wrong. But question is, if we really need like 100% data, in some cases yes, but I guess these companies have completely different strategy how to avoid it. But normal companies, they can usually live with some small data losses. It doesn't sound good, but it is practical, and I think this is the best answer I can give you. Yeah?
Hi, thanks for the talk. We use checksums on all our databases, and we use PG backrest to back them up daily. And I've relied on that to be a good check to find corruption quickly. Is there anything else I should be doing?
To be honest, I have tested very simple examples. So I think you have more lines of defense, and depends, of course, what file system you have on your disks, how you actually store those wall logs and so on. So from my perspective, if I would run a company which can actually live with some data being lost or whatever, then I would say yes. But if you are running some highly critical business, bank or whatever, then you will probably do much more. So yeah, this is all I could tell to this thing. Yeah.
You relied on a segmentation fault to tell if a tuple is corrupted or not. But this will work only in cases where you get an invalid address, when you're referencing an invalid address for a tuple.
Yes.
But we can have situations where a wrong offset can result in a valid address,
Yes.
but not belonging to the real tuple. So the consequence could be wrong data restored. Can you think of any additional scenarios what to check in such cases?
Yeah, this is a good question, and I tried different options and tried also situations when I did not damage those system columns in the tuple and damage just data content. In some cases I got errors that, for example, value is not fitting or whatever, but I did not gather enough data, and I did not have enough measurements to derive some clear results from it. So I would definitely try to do it again. But you know, the deeper we go into that structure, the more complex it is. So I have some results, but I don't want to publish them yet because it's not repeatable enough, I would say, from my perspective to document it in that talk.
Okay, thank you for that excellent talk. I just want to mention that's a great idea to have a backup software that calculates the page checksums because we can detect it very soon if something is wrong. But still, we will not cover everything. Imagine that by a software issue, we will write the block to a bad file with a correct checksum, and nothing will help you. So there's definitely not solution for everything. But still, it's good to have them turn on.
Yeah, this is very, very good point. Yeah, thank you.
About the zeroing the page, if I'm sure that the page is corrupted on disk, then okay, I can fix it. But many times it can be corrupted when reading, corrupted in memory, but maybe on disk it is okay. So before zeroing, do you try to read it again, restart the instance and read it again? Or, I mean, it's very difficult to know if it is really lost from the disk or if you read from a cache where it was corrupted only when reading once.
Yeah, well, I tried to analyze this situation because also people in Berlin ask about it. So I presume that if that page is in memory, yeah, well, actually it could be actually also rejected by Postgres and it will be still in memory. Yeah, that's what this...
For example, we could imagine that it would be better to crash the instance and then it restarts and rereads.
Yeah, this is a very interesting corner case. I completely agree. And I think it deserves to be tested in some way. I just don't have any code for it to really like inject something in a memory cache to try it. But like theoretically, I think you are completely right. Because there could be something wrong with that memory part where that page is actually stored when it is taken from the disk, and we can have right data page on disk and corrupted version in that memory because of that memory fault. And once we ask for it, we actually read that corrupted page from memory. Yeah, well, this is very difficult corner case. To be honest, maybe this asynchronous I/O actually, if I understand correctly, in some cases can avoid this memory cache. So maybe with this asynchronous I/O, we have like better chance to avoid these cases. So, but yeah, maybe you can tell more. No, please.
No, it still goes to shared buffers.
Yeah, the truth is that also shared buffers could be damaged. But if some part of memory will be damaged, I think we will see much bigger problems than just this one case. So at least I hope so that it will actually prevent Postgres from running. So.
If this is a frequent case, do you see any market potential for building services or product around your work?
Yeah, well, it strongly depends on companies which actually face this situation. Because if you are some very small accounting company using some software which runs Postgres behind the scene, and you are running some very tight business, you know, you do not want to spend too much money on these things. This is why we had to come up with solutions which were quick to execute and give those companies as quickly as possible those data. So small companies will probably always vote for some free open source tool. But I think there are big companies which can also face this situation from time to time, and there would be a bigger space to develop something which could then be beneficial for the whole community. And I know companies which even are willing, you know, to contribute to community this way. So once they will face this situation, who knows, you know. This is at least how I see it in our work.
So are checksums checked during replication or validated during replication?
Checksums are on data blocks, so I think replication sends those vol logs, and they are applied as they are, and if everything is okay, then no error happens.
All records always have checksums.
Sorry?
All records always have checksums.
Okay, yeah, so... Yeah, sorry, yeah, I was thinking still about those checksum data blocks, thank you.
Okay, this is the end. There will be half an hour of a coffee break, and afterwards there will be lightning talks over in Omega.
Thank you.